So this first introductory lecture is called Ghost Chasing, which was when I came to CSUN to do my interview for the job here. I was asked to do a teaching talk and a job talk. So my teaching talk was actually on SEM, and I delivered it to a class of students, and it was I called it Ghost Chasing: An Introduction to Structural Equation Modeling, which this lecture sort of follows that pretty closely, except I added some stuff and tweaked things a little bit, and I changed it to latent variable modeling to make it more sort of inclusive of other types of models beyond just structural equation modeling. But this name Ghost Chasing I had stolen from a professor at UCLA named Jim Sedenius. And I think at some point I had told him I had stolen the name, and he sort of laughed and said that he had stolen it from somebody else too. But it's a pretty apt analogy for what it is we do in psychology and social sciences in general. We chase ghosts. So this lecture will cover like ghost chasing and latent variables. We will talk about structural equation modeling as a framework for looking at latent variables. We'll talk about the elements and jargon around SEM. We'll go through an example of some SEM models and talk about the broader sort of SEM family of models that you can perform. And then we'll switch over to talk about IRT, which is it's item response theory models, which is another form of latent variable model. It's oftentimes referred to as a latent trait model, but it's the same basic idea. So we're looking at latent indicators of a latent variable. We'll talk about some jargon there, and then go through some example IRT graphs. So what do I mean by ghost chasing? Psychologists are in the business of chasing ghosts. So when I think about the kinds of things we try to study in psychology and in social sciences in general, I think about those shows like Ghost Hunters and those kinds of shows where they go to places and they look for evidence that ghosts are present there. They look for things like EVPs, electronic voice phenomenon, and cold spots, and where they have like drastic changes in temperature, sounds and noises, and the presence of electromagnetic fields and things that can make people feel so nauseous or uncomfortable. And they use those collectively to make the argument that those things indicate that ghosts are present. Now, most of those episodes, if you watch them, they often, conclude that ghosts are not present, that they find these things, they find sources of these phenomenon, and they're usually rooted in something very, very real. Sounds are usually pipes or something that changes in temperatures because there's a ventilation duct or something that is blowing air in a certain place or something. They find some reason to explain it in a way that isn't ghosts, but the process is sort of the same. We try to measure ghosts. Like we take something like depression, and we look for behaviors that we can measure directly that we feel are indicators that depression is present in an individual. We all sort of agree that depression exists. We may have slightly different definitions and things, but in general, we agree that depression is a thing, or like anxiety is a thing that we're trying to study. And we look for ways of trying to measure those things. So the ghosts are these sort of unseeable, at least not directly, metaphysical things that we are trying to study within psychology and social sciences in general. And we try to measure them. We try to figure out ways to get at them, to study them. We even use ghosts for diagnoses. And we look for traits in individuals that indicate they have clinical depression or clinical anxiety or something, or schizophrenia. Okay, we exchange one ghost for another. Oftentimes we'll, in the, like with diagnoses, we'll, have a diagnosis of one thing that then gets traded out for something else. When we actually learn more information, we actually sort of exchange one thing for another. We tend to talk about things that don't really exist. And at one point, I remember giving a lecture or something where we started talking about that there's a lot of similarities between fields like psychology and social sciences and things with like religion, that we believe in these things. We sort of have a certain amount of faith that these things exist, and we talk as if they are tangible, real objects. And I don't mean to disparage the process here. I think I'm not saying it's a negative when I say that it's like a religion. I just mean that collectively we've all agreed, we've decided that such things exist. These latent variables exist out there, and we're doing the very, very difficult job of trying to measure them, trying to study them. Often, the way we do that is in a very narrow way. When we have a single question or something, are you depressed? On a scale of 1 to 10, how depressed are you? And those have their utility because there's sort of simplicity to it. But this process of latent variable analysis allows us to get a broader bandwidth of what those things entail and how we can measure them and study them. And it ends up being a much sort of richer approach to how to study these things. So the latent variables, these ghosts we're talking about, is anything that can't be measured directly, that we need to try to get at indirectly through measured indicators and looking at a host of combined behaviors or combined responses to really get at the underlying mechanisms that are driving those things. And we call those mechanisms latent variables, right? Just like depression or anxiety, we look for patterns of behaviors that sort of coincide with a certain diagnosis or a certain mechanism that we've identified, and we study those things through those identifiable indicators of that phenomenon. So what do we think about when we think about latent variables? It's just a more sophisticated form of operationalization. We're going to take data and we're going to operationalize the data with this abstract construct. So it's a data reduction method that uses regression-like equations. We're going to take many variables and try to explain them with one or more factors, latent variables, latent traits. We're going to try to group behaviors, indicators, answers to questions on a survey, and we're going to try to explain all those responses with as few things as possible. And it's those few things that we're going to label our latent variables. We're going to do this by taking correlated variables, and we're going to group them together, and we're going to separate them for variables that aren't correlated. And this sounds, and it should sound, very much like exploratory factor analysis, where most of you, we talked about this in 524. Multivariate analysis, and it's the same process. It's just we're going to take a broader look. We're going to expand the way in which we do this process to include a lot more methods to sort of get at the latent variables besides just exploratory factor analysis. We can establish latent variables in a couple very general ways. There's probably more than this, but just in a very general umbrella terms, there's two different approaches. One is through a sort of factor analytic approach. I mean this sort of broadly, where our outcomes are continuous, and we're trying to use things like Pearson correlations and things to group items together and find out things that are related. The other way that we haven't spent a lot of time on, or haven't spent any time on, is an approach called item response theory or item response models, where if multiple regression was extended, you can see that as factor analysis being an extension of sort of traditional multiple regression. Item response models you can think of as the same kind of extension for logistic regression models. So the items are no longer continuous. There are things like dichotomies, ordered polynomous items like 0, 1, 2, 3, 4 or something, where it's not a complete continuum. And it allows us to try to capture things like probability. So again, with logistic models, we're always trying to predict probability of things. We're going to do that with item response models, which makes it very different. It's a non-linear approach to prediction, just like logistic regression is. So down here, I just a little note, like I'm treating these and I'm talking about these as separate topics, which in many ways they are, and they sort of originated from different fields and for different purposes. But in the last decade or two, the differences really have started to blur. And a lot of times they're sort of interchangeable. If we do a factor analysis, but we have dichotomous items, right? It starts to blur. There's actually things we can do to do that, to actually make that work. And it starts to blur the lines between what is a factor analytic model or an item response model. And we'll talk about some of those differences more in detail later on, but they sort of originated as separate things out of different fields. Like IRT grew up in things like educational testing, so it had sort of a different purpose, and there's more things going on with it than is found in a typical factor analysis. So even though I'm treating them as separate, and we're going to talk about them as these different topics, there's a lot of overlap, and that overlap in the sort of gray area between them has become a lot narrower, or a lot more overlap, or the difference is a lot narrower in the recent past, especially with programs. Just thinking one in general, M+ start off as a sort of latent variable modeling program, M+, and it started off just like EQS or other SEM programs, but then sort of started to really be more of a general latent variable modeling approach that included all kinds of other things that other programs really didn't do. And that includes IRT. So you can do IRT models at M+, you can do, because again, the lines, the differentiation has become blurred. And a lot of this is because of the research and advancements of these kinds of models, these sort of general latent variable models or latent variable approaches that was done by a man named Bengt Mutane, who is behind the M+ program. It's actually him and his wife, I believe, Linda Mutane. So oftentimes the program is Mutane and Mutane are the sort of authors of the program. And so he was a professor at UCLA in the College of Education. He's since retired and pretty much has spent like his whole life is basically the M+ program. So it's a very powerful program. It's one that like Sarah Brzezinski has used in the past for this particular course. And there's a lot of pluses to it. There are things I don't like about it. We could talk about those things later on. One of which is the cost. It's a program that comes with a yearly subscription where we're going to stick to using R for now, and which is free, which is is a nice sort of bonus. But keep in mind, M+ is a program with a huge sort of fan base to it. There's other programs like EQS that has its own sort of fan base. And there's even more. There's AMOS, which is a companion program to SPSS that also does does SEM modeling. There's lots of them. But we're not going to talk about most of this. We're going to stick to R, talking about the sort of free packages that R provides for doing this stuff. So latent variables can be established, like I said, through the factor analytic or item response theory models. You also think of it in another way. We can establish them in exploratory ways, like we did in Psy534 with exploratory factor analysis, where the structure of the atoms may not be known. Like you may know the atoms go together, but you don't really know how, like how many factors and exactly how they might go together. So you might do a more exploratory method. So data is sort of summarized, grouped together. It's a way of investigating sets of measure variables for underlying constructs, underlying latent variables. It's often done more at the sort of onset of research and or like scale construction when it's being designed as part of the like validation procedures. So things like exploratory factor analysis, but there are sort of newer approaches that I'm not even as familiar with because I've only played around with them a little bit, that are exploratory structural equation modeling approaches to doing exploratory models that take a different approach than factor analysis, but the end is sort of supposed to be sort of the same in terms of trying to identify underlying constructs when the structure is more or less unknown. The flip side of the exploratory stuff is confirmatory models or confirmatory methods, which is what we're going to talk about in here. Confirmatory methods, we're going to test whether proposed constructs and fluids measured variables. So proposed means I have to have some idea of how they go together, right? I have to have a theory, hypothesis about how items go together on factors. When measurement structure is known or at least theorized, so we're going to talk about this more in a second, but the measurement components of a model is the factor analytic part. So we actually have to know what the measurement component looks like. So this is confirmatory factor analysis. This is also in structural regression models. And item response models are typically thought of as a confirmatory method. Okay. And this is how we generally conceptualize, at least visually, what a latent variable model looks like. And we can think of this generically for any of these. It doesn't really make a difference if it's exploratory or confirmatory, SEM, IRT. You can sort of think of this as this is the same in general. IRT will oftentimes have a little bit more to it than this, but in general, this is a way of thinking about it, that the latent variable is driving the responses to the items. So the errors are going from the latent variables to traditionally, sort of conventionally, a circle to these squares that are the measured items. So think about, you know, our analogy with ghost hunters, right? It's the ghost, right, that's supposed to be making the noise, or the electric voice phenomenon, or changing the temperature in the room, or whatever ghost indicators you like. So it's the ghost, right, that's driving or creating or you know, pushing all those sort of indicators that they're present. It's the same thing. If this is depression, it's a person's depression level that's driving the response to each of the items on a depression inventory. Okay, so it's not the other way around. Not that, you know, their response somehow gets put together into the depression. It's their depression that's really driving it. That's what makes it a latent variable. It exists. It's there. We just can't see it. And it's actually having an influence on a person's behavior. So I've mentioned SEM. So SEM is structural equation modeling. Those sounds a very fancy term. Sometimes people call them SEM models. It's a little bit redundant because we oftentimes call them SEM models, which got the word model right in there, but they're structural equation models. The term SEM, or structural equation model, is often used interchangeably with latent variable model, but they're not necessarily the same thing. SEM is one sort of approach, one framework to estimating latent variables. It's also referred to as covariance structure analysis. I actually like this name because it's often what we're doing with an SEM model is trying to put some kind of structure to the relationships, to the covariances between items. So a covariance structure analysis actually seems a lot more explanatory of what it is we're doing than, say, a structural equation model. It doesn't really describe what we're doing very well. There are also names like causal models. So causal model and path analysis are oftentimes used interchangeably, where they're both a sort of subset of a type of SEM model. Path models are like regression, right? They're measured, it's all measured variables and looking at the prediction between them. It's not the same thing as a confirmatory factor analysis where you actually have factors, okay, or a latent variable model. One of the reasons why SEM and latent variable models aren't the same thing is because not all SEM models even have latent variables. You can have a structural equation model that has no latent variables in it at all, and it's still a structural equation model. It's oftentimes called simultaneous equations because it's oftentimes, when you see it, there are a bunch of equations that are all being solved sort of simultaneously. So a simultaneous equation makes sense. And then also, you know, again, people do refer to it as latent variable modeling. These different names oftentimes come out of different places, whether it's coming out of the same kind of model coming out of economics or coming out of social sciences versus education. A lot of times they're the same types of models or similar models that have different names for the same exact thing. Right? So what is it? What is an SEM model? Well, it's a combination. It's like we're combining what we do with regression with what we do with factor analysis. When we do an exploratory factor analysis, we're able to get back some identification of the factors that are present, and maybe they're correlated, maybe they're not. Right? We either have an oblique rotation or an orthogonal rotation. But what EFA doesn't do is allow us to say, well, I have these 4 factors. I want to take factor 1, and I want to use that to predict factor 3. And I want to take factor 2, and I want to use that to predict factor 4. We can do this in SEM. We can actually combine this idea of latent variables and actually conduct regression type equations amongst the latent variables, which is a crazy idea because already we're talking about trying to identify a variable that doesn't exist. Right? We're going to create this thing. We're going to look. Here's this ghost. We're going to manifest here. We're actually bring it out and study it. Now let's see if this ghost predicts that ghost, and we can actually, estimate slopes and coefficients to actually measure those predictions. It's like mind-blowing stuff that we're able to do this, and it's actually really cool. Once you get into it, get used to it, you can really see like, man, it just opens up the doors for all kinds of hypotheses that you may have never thought were even possible before. So what we're going to do is we're going to specify models that explain data with few parameters. We're going to try and take a bunch of parameters, just like EFA. We're going to have a bunch of correlations, a bunch of relationships, and we're going to try to explain a bunch of relationships with as few factors as possible. It's very flexible. It works with continuous and discrete variables with some corrections. So we actually can have discrete outcomes. You might be thinking, well, doesn't that make it IRT? Sort of, but not really. There's just corrections we can use, things we can do to actually make it a better estimation when they're categorical, non-continuous items. We can do significance testing of all the coefficients, so a slope or correlation or that kind of thing that's in the model. We can test those individually, but then we can also look at the model as a whole and do model fitting, right? So we can actually see, does the model actually fit the data? Typically, models, SEM typically models covariances only. So I say typically, and depending on where you sort of come from. So I learned SEM via sort of EQS, and that sort of field through Peter Bentler. And in EQS, the assumption when you run an EQS model is that you're going to run a covariance structure analysis. You're going to only be modeling the covariances. Or M+ that I just mentioned a second ago, it makes the opposite assumption. It assumes that you actually want the mean structure, which we'll talk about more later on, that you don't just want covariances, you actually want the levels, you want the intercepts, you want the means as well, and it assumes that you're going to run it that way. And you have to tell it not to do that. Or in EQS, it assumes you don't want it, and you have to tell it to do it if you want to do it. So it depends on sort of not field, because it's oftentimes the same kind of stuff, but it's not like it's education versus psychology. It's just what way you were sort of taught to do it. But most programs start off assuming you want covariances only, and then you could add mean structure. And again, plus maybe one of the only ones that does it the other way around. I could be wrong. I may have changed since the last time I've checked, but at least that seems true. So in sort of continuing with what is SEM, SEM has there's two parts. There's the measurement part I mentioned a few slides ago. The measurement part is really the factor analytic part. It's the part that relates indicators, items, measured items, to latent variables. And that's the measurement part. And that fits, because you talk about measurement theory, like psychometrics. It's really about trying to identify these sort of latent variables and things. So it makes sense that that's the measurement component. And then you have the structure or the structural part, which is looking at it's the model that relates variables or factors to one another. So this is the prediction part. This is the regression component. This is what allows us to take one factor, one latent variable, and predict another factor with it. Right? So we can actually have predictions and things. So that's the structural part. Now, if you have a model that's all measurement, no structure, that's a confirmatory factor analysis. If you have a model that's all structure, no measurement, that's a path analysis or path model. And when you have them together, it's thought of as a structural regression model. Again, you don't need to memorize all this stuff. This is just laying the groundwork for stuff we're going to come back to later. And then it'll sound a little bit more familiar because we've already talked a little bit about it. So when we revisit it, it'll actually ring a bell a little bit. Sound a little bit less scary. I don't know. So looking at the basics of a conventional SEM model, and again, there's some flair that gets added to this in certain types of models, and we'll talk about those things as we go on. But the basics are, if you see a square in the model, it's considered a measured variable, something that was directly measured. Sometimes these are called manifest variables because they're the things that are actually visible. They're manifested. The circles are considered latent variables. So each time you see a circle in a diagram, that's the latent variable we're trying to measure. Single-headed arrows are either, this is where things get a little bit confusing, a regression weight, like a slope, or a factor loading, depending on where it is in the model. If it's an arrow going from a circle to a square, then it's a factor loading. If it's going from a square to another square, it's a regression weight. If it's going from a circle to another circle, it's also a regression weight. So it depends on where it is, but it's basically some form of prediction. And then any double-headed arrow is considered a covariance or a correlation. It's also considered unstructured. So to have structure, remember we have measurement and structure. Structure requires direction. Right? You have to have a regression weight or factor loading. Well, you have to have a regression weight for it to be structure. So it actually has to be one direction. If it's a covariance that is bidirectional like this, then it's no longer considered a part of the structure. It's considered an unstructured portion. It's basically saying you could have put in a prediction here for the direction and you didn't. So it's basically like you're saying, I don't know what the direction is, and you're just putting a covariance or correlation in its place. So it's unstructured. All right. So here's some examples of path models. This is structure without measurement. Okay, structure, no measurement. So you see no circles, 0 circles in these pictures. And so if you go top left here, what kind of model is this? You have a predictor, you have an outcome. It indicates that the arrow in the middle here is the slope, and you have error out here. And this is not measurement error, but the error in prediction. Okay, this is a prediction error. This is basically the part of y that isn't x. Right, it's the leftovers. Right, so it's really an error. This is really just a simple linear regression. Right? It's simple, even though it's just looking at the slope. There's no indication for the intercept here. It's basically just a simple regression. One predictor, one outcome. All right. And down here at the bottom, you now have an x, you have a y, you still got the e for y, you got the slope of y predicted by x, that's great, but you also have z in here, where you got z predicted by x as well, and you also got that y is also predicted by z. Z has its own error as well, because x is predicting it, then this is the part of z that isn't x. This is the part of y that isn't x. Right? And actually, technically, this is because we have z predicting it as well here. This is the part of y that isn't z or x. Right? Both of them in there. So because this has both a direct effect of x on y, it also has an indirect effect on x on y through z. That's both direct and indirect effects. This is basically a diagram for a mediation model. All right, so this is mediation. In path analysis terms, we usually think of it as indirect effect instead of a mediation, with the same basic idea. So what do we have here? Now we have two x's predicting y, and then it looks like we have the x's multiplied here, and looking at its influence on y as well. So since this is sort of mediation, this is sort of the other side that people get them confused a lot, which is this represents moderation, because another term for moderation is an interaction. Okay. Interaction effect. I want to see what's the direct effect of x on y, on x2 on y, but I also want to know if the two of them together are impacting y in some way that is more in addition to x1 and x2 alone. So you can think of, is x2 moderating the effect of x1 and vice versa? We can also think about moderation in a different way, and we'll get to this as we go forward, that I can establish a relationship like this, and this is something we typically do. We think, okay, I'm going to take x and predict y. But what if I had a hypothesis, not that, say, men and women were different on average or something like that when it comes to something like, I don't know, whatever, let's say this is depression and anxiety, right? I don't think they're different in average. I think they differ in terms of how much depression predicts anxiety. I think, let's say for women, the relationship between depression and anxiety is going to be stronger than it is for men. So I can test this sort of moderation effect differently. I can actually create a model for this that is for both males and females, model them separately, and then compare the slopes of those two models, as well as the error and even the variances of the variables, to see if those things differ. Now, we're not talking about differing in terms of how much they are depressed. We're not even talking about that. We're not even talking about the levels. We're talking about, my hypothesis is, I think gender moderates the prediction of anxiety by depression. Now, it's a different hypothesis altogether. It's still moderation, but it's thought about in a different way. And we can do that in SEM through a process called a multi-group model or multi-group analysis. You can actually establish these models in multiple groups and then compare them to see if there are actually significant differences across these coefficients. And that's a very different type of hypothesis than we're used to. So here we have a measurement-only model, sort of the opposite of a path analysis. Here we have all sort of factors, latent variables with no structure. So again, these are double-headed arrows to let us know that the factors are correlated, but that means that they remain unstructured. All right, so we have a bunch of indicators, measured variables, and the only way that they relate to anything else in the model is that they are providing the measurement structure for the latent variables. If we were doing this as an EFA, this would be the same as doing like a three-factor exploratory factor analysis with oblique rotation, right? Allowing the factors to rotate obliquely, let them correlate. If we set these to 0, these correlations, or if we just got rid of them altogether, then it would be it'd be analogous to an orthogonal rotation. Okay. Here we have a structural regression model that has both structure and measurement together. So we have some measurement in the form of sort of factor 1 and factor 2. And then we also have, even if I just put this one arrow from factor 1 to factor 2, that would mean that there's structure, right? But we also have variables that are only measured. These aren't part of any sort of measurement model. They're just measured variables on their own that are predicting each other. So we have one going to another, an x to a y here. we have this measured variable predicting a latent variable, and then the latent variables predicting each other. We even have this measured variable predicting this. So anytime you see a variable getting predicted, like an arrow comes to it like this, there's going to be an error. That's an error in prediction. Even though it's the same kind of thing, because the factor is predicting this error actually is the unique variance. It's the measurement error, not the prediction error. It's the measurement error, the unique variance of this item. It's the part of Y3 that isn't explained by the factor or that isn't common with the other items. Okay. You also notice there's a D1 and a D2. So what could those be? Why would we need a different letter? Well, the D's here really represent the same thing, the same idea as the E's, right? It's because I'm taking X1, I'm predicting factor 1 with it. F1 here is actually being predicted. Anything that's being predicted requires an error. There needs to be an error in predictions. So this D1 represents the part of factor 1 that isn't related to X1, right? It's the prediction error in predicting F1 from X1. This is the same thing. It's the prediction error predicting F2 from both Y7 and F1. So these two things are just the errors that are associated with the factors, and they're labeled as D because they're oftentimes called disturbances. That sounds weird. The first time I heard that, I'm like, what? It's really just it's a prediction error related to factors. So once a factor is being predicted, it has an associated disturbance. So factor 1 has disturbance 1, factor 2 has disturbance 2. That's it. Okay. We can actually assess this model all together, looking at the significance of the predictions, looking at the quality of the measurement components, and look at it all sort of holistically, and at the same time looking at the significance of all the individual coefficients. Okay. So what are the goals in SEM? So obviously we're trying to build these models and see if they are correct and to test them. So we want a model that has a number of parameters less than the number of unique variance-covariance entries. We're going to come back to what this P times P plus 1 divided by 2 thing is, but this is a really simple equation for figuring out how many things in a covariance matrix are unique. Because we talked about before, with correlation and covariance matrices, the components repeat, right? So the bottom diagonal of a correlation or covariance matrix is the same as the top diagonal, right? So there's lots of components in a matrix that actually are repetitive. So we don't want to include the repetitive components. We want just the unique things. We're gonna do that. We're gonna actually create a model, right? We're gonna create some model like one of these pictures, right? We're going to create some model like this that we think it explains all the relationships. And that's going to create an implied covariance matrix. So implied, because it's implied by the model. We're going to create a model. It's going to imply then a covariance matrix. And then we're going to compare that model-based covariance matrix called sigma theta. We're going to compare that model-based matrix to our actual data, our matrix from our data, which is our sample covariance matrix S. If our model is perfect, like it explains everything perfectly, then all the differences between these two matrices should mean that I have zeros everywhere. It's going to explain everything, right? So as the differences between these start to become non-zero, start to become actual values, that tells us places where the model is not doing a very good job of capturing parts of the covariance matrix. It allows us to estimate population parameters to make the sample data most likely. So it's a little bit reverse thinking. We have a sample. Our model is supposed to represent what we think is really going on in the population. So we create a population estimated to a matrix, a sigma theta, based on our model. And we want to see, does that match what we see in our sample covariance matrix? So just to give you an idea, like this is the S matrix. So in the diagonal we have variances, All right, so this is a covariance matrix. So the middle diagonal here is all the variances. It's 1 with itself, 2 with itself, 3 with itself. Anytime you take a covariance of a variable with itself, that's a variance. Okay. And then the off diagonals here, these parts, this is the covariance between item 2 and item 1. This is covariance between item 3 and item 1. Covariance between item 4 and item 1. Item 4 and item 2. Item 4 and item 3. Item 3 and item 2. All of those repeat up here. So when looking at this matrix, how many things are unique? Okay, so I have 1, 2, 3, 4 variances. And I have 1, 2, 3, 4, 5, 6 covariances that then repeat. So I'm not gonna count that as 12. I'm gonna count that as 6 unique covariances and 4 variances. All right, so that means that this has 10 unique components. Right? 10 things that are not repetitive. If we think about the number of items we have as P, we can use that equation to figure this out. P times P plus 1 divided by 2. All right, so 4 items times 4 plus 1 is 5 items divided by 2 equals 4 times 5 is 20. 20 divided by 2 is 10. So this little equation will tell us how many unique things we have. How many things do we need to try to explain? Right? These are the things that we're trying to capture with our model. So I know I have 10 different things, elements in my matrix that I'm trying to explain with the model that I'm going to be creating. So I'm going to create a model. It's going to create this sigma theta matrix. So again, it's going to generate variances and covariances based on the model that we put together. That's why it's called a model implied covariance matrix. And it's model implied, but it's also what we believe is going on in the population, right? It's the real deal. It's what's really happening. And we're going to try and see if this model implied matrix really does fit or match our actual data. We can actually take and subtract these two matrices component by component. I can take the variance here, right? Subtract the variance, these variances because they're the same. This covariance and that covariance, right? I can actually do it component by component. And what I'm going to get is called a residual covariance matrix. I'm going to get the differences. If this perfectly recreates our sample, then the residual covariance matrix will all be zeros. If it doesn't, there'll be non-zero components, so we can figure out what's missing from a model. It's actually not capturing some part of that covariance. So like anything, this is going to have a bunch of jargon. And sometimes it's going to sound overly complicated when it shouldn't. This is like the simplistic view. So we say model specification. Okay, model specification really just means translating the thing that we want to test, our model, into equations, right? Specifying a model. So we want to take this thing and make it into some kind of testable equations, testable things that we can actually turn into a model implied covariance matrix. So oftentimes just creating this diagram, right, just doing this is specifying our model. That's model specification, right? It's saying this is what I think the model is. Model specification. Model estimation is the part that's probably the hardest part. It's the part that actually requires the most sort of math. It's the part we're not going to get into very much. We're not going to spend a lot of time going through how to do an iterative expectation maximization procedure, okay? We're going to trust that programs like Lavon or packages like Lavon and R are going to do that for us. But it's really when we use things like ordinary least squares or maximum likelihood to actually calculate the parameters, to estimate those covariances that we want in our model. It's what's going to do that for us, to estimate the coefficients, estimate all those things that we are trying to estimate. It's going to do that for us, sort of in the background, sort of black box. Okay, we'll talk a little bit about what it does and how it works, but we're not going to get super crazy in the mathematics. So model identification is probably the trickiest of them, where these are rules that we'll talk about for how to make sure that your model can be estimated. So estimation is the procedure of going through, like, OLS, maximum likelihood of actually getting our coefficients, our slopes, our loadings, all those things. But there are rules for how to make sure that that actually can happen. I want to talk about those. Things like making sure you have at least 3 indicators per factor. That you have to set either one indicator to 1 or the factor variance to 1. There's these sort of rules we'll talk about when we get there. Okay, that's what model. So is your model identified or not? You got over-identified, under-identified, just identified. We'll talk about all those things that'll make total sense when we get there. But that's sort of another jargony thing you hear a lot when it comes to SEM, but model identification. Then you got model evaluation. So now you've specified a model. It's identifiable. You've estimated all the stuff. You've ran the calculations and things, and now you're trying to see, well, how good was it? How good was my model? So comparing observed and model-based covariance matrices to look at model fit. Now we're talking about fit indices and all kinds of other things that tell us whether or not our model actually explained the data well. We're looking at the significance of individual parameters. So we're going to look at model evaluation in 2 different ways. We're going to look sort of narrowly at each of the parameters we estimated, like the slopes and loadings, to see if they're significant. But we're also going to look holistically at the whole model to see, does this model represent our covariance matrix well? And we're going to use things like chi-squares and these other things like log likelihoods, which would sound familiar from logistic regression stuff, to actually test whether or not that model fits, okay, and how well it fits. So structural equation models with latent variables require that researchers at least consider how the construct is measured. We actually have to know something. And I'm saying this, it seems like I mentioned before, but SEM is not exploratory. Right, it's not something you're going to start off knowing nothing and just sort of piece together a model, piece by piece. You must have some theory or hypothesis or previous results about how latent variables are to be identified. There has to be something known. You can't just sort of stumble into this blind. So if you are blind to sort of what's going on and how the variables are going together, then go roll back to exploratory factor analysis. Start there. And then once you sort of start to have an idea of how things are going together, you can then move forward to something more confirmatory. Researchers are also required to test the entire model. So unlike regression, where you can just throw out things are related and put your regression models out there and report significance, if you're doing something like a path model, you're going to have to include how well the model fit. Oftentimes you'll be required to fit alternative models to one another, see if those models fit as well. All kinds of stuff that actually goes on. And this reduces the reliance on testing individual hypotheses sort of separately. So you got to look at model fit and what did you do to make your model fit? Did you actually do model modifications, which are things you can do to actually make your model fit better if it doesn't fit well initially? And sometimes, again, I think my model, like go back to our picture again. I think this is how, the model works. And someone's like, yeah, well, what if, maybe it's, maybe Y7 is really the predictor, X1's the mediator, or, maybe it's, the F1 and F2 are really predicting these outcomes or something. Maybe Y7 is really just another indicator of F2. So you can actually test a variety of alternatives to see if those models fit as well as your original hypothesized model and compare them. And if your hypothesized model is actually the better fitting model, that's more evidence that your model may be the correct one. So SEM, again, is not a single technique. It's like a family of things. It's a framework. And assessing the fit of hypothesized models to data. So as a family, it has some shared characteristics, but then there are some things that are different. So it's definitely an a priori sort of approach, but it's not complete. I'm saying it's confirmatory. It is it's confirmatory to a point. You have to know enough to be able to run a confirmatory model. And if that model doesn't fit, you can tweak things, modify your model, and explore ways to improve your model. But you have to have something, a base with which to stand on to start with, okay? You can't just start off with nothing, the clean slate, and have the computer tell you how things are related. So SEM can blend exploratory and confirmatory procedures, but it has to start off confirmatory, and you actually have to be able to start off at that point with a confirmatory model. Some other shared characteristics, like there's an explicit distinction between observed and latent variables. However, latent variables are not required. All right, so again, this is a latent variable class, but we're going to spend a good deal of time on path analysis in which there are no latent variables as a way of sort of building up to doing more structural regression models and things like that. Many types of latent variables reflect different, there are many types of latent variables. They reflect different assumptions relating observed and latent variables together. Latent variables can represent different phenomenon. So sometimes there could be person effects, method effects, clustering of items effects that are different than, say, the factors you may think of. We'll talk about what that means, but let's say we're used to thinking about factors as like items that have similar content or measuring the same thing go together. But sometimes maybe if you give someone a clinical interview, a paper pencil test, and they also then take some kind of cognitive, computer-based test. What you may find is that there are items that are content related. So certain things across the way in which they're measured are grouped together as sort of content factors, which is what we're used to. But then you also may get that all the items on the clinical interview cluster together or factor together separately as a method factor, or all the items on the paper pencil test go together because of the method in which they were collected. Same thing with the cognitive battery on a computer or something like that. So sometimes you get these clusterings of items for different reasons. Sometimes it could be a method effect or something like that. The observed latent distinction also provides a way to take account of imperfect score reliability. That's something that's interesting too, is that we know that items are not measured perfectly, never. The reliability often is never, I think almost never perfect. And what the factor analysis allows you to do is to remove those imperfections in the items. So when you're looking at the factors, all of that messiness in the items gets removed. So the factors tend to represent purer, less error-prone, error-riddled variables. So when you're actually going to do things like predict one another, you're getting cleaner predictions, cleaner regressions, because all of that measurement stuff has been removed. So again, all SEM models sort of have this thing where the variance covariance matrix is the basic unit of analysis in SEM. However, other types of data can be used, such as means. So later on in the semester, we're going to talk about mean structure analysis, incorporates the levels, the means, and the covariances together into the same analysis. And you can do both prediction and differences in mean, like ANOVA type comparisons, all at the same time. So it's like regression mixed with ANOVA simultaneously, which is pretty cool. It also possible in SEM to test for group mean differences on latent variables, which again is crazy to think about. Latent variables don't exist. Hey, let's create one. And we're going to create a mean for everybody on those things, and then we're going to compare the means on these things that don't exist. Pretty crazy. All right, something that is not really feasible in standard ANOVA, because we're in standard ANOVAs we're dealing with sort of measured variables only. All right. The technique of SEM is not just for non-experimental data. It's typically most of the time it's used with correlational data. I have a bunch of stuff I think they're related in this way, but it doesn't have to be. Instead, it's a very flexible analytic tool and can be used with experimental data. It can be used in lots of ways. The only limitation with it oftentimes is just your the way in which your data were collected, right? So if you actually collect it in an experimental way, which things are manipulated, you can actually do the analysis and actually have causal conclusions the same way you would with ANOVA or MANOVA or all those things. It just depends on how the data was collected. It's often associated with correlational data because that's the type of data that it gets applied to most often. It doesn't have to be that way. Many standard statistical procedures, including ANOVA, multivariate counterparts like MANOVA, profile analysis, and that kind of stuff, can be viewed as special cases of SEM, and really can all be done within the SEM sort of framework. SEM is still generally a large sample technique. So just like with factor analysis, when you're trying to estimate a bunch of parameters, you need a lot of people to be able to find them. With n less than 100, almost any type of SEM analysis may be untenable unless a very simple model is evaluated. For descriptive purposes, sample sizes that less than 100 could be considered small, between 100 and 200 subjects, or sort of medium is a better minimum, but model complexity must be considered. Sample sizes that exceed 200 cases can be considered large. It really depends. Small, simple models require fewer subjects. Larger models considered need more. This is a little bit dated now. In 1992, they were looking over a bunch of SEM. It was like a meta-analysis, and found that of 200 studies, of 72 studies, the ends of those studies, the average was about 200. So you're sort of looking at about 200, for a publishable model, but it's 200 or more, with emphasis on more. And the more complicated the model is, the more subjects you have to do it. Another part of the shared characteristics, it is possible to test many different types of effects for statistical significance in SEM, but the role of the statistical test in the overall analysis may be less important. Right? It may not be as important compared to the more traditional model fitting techniques. So what is this verbose piece really saying? Yes, we can look at the significance of each coefficient, like the slopes and loadings and things. But that's probably not going to be as important, or it definitely won't be as important if the model doesn't fit very well. So the model fitting, the fact that our model is explaining the covariances and things that we have, is often seen as more important than the testing the individual coefficients in the model. So if the model doesn't fit, the coefficients oftentimes are ignored. It doesn't really matter if they're significant or not, because they're not doing a very good job of explaining the data. Basic SEM models, which you'll see include some not so basic things, are what we are going to focus on, the sort of nuclear family, the basics of SEM. The outcomes are typically continuous, normally distributed. This should sound familiar. It's the same as it is for all the MANOVAs, all the ANOVA stuff we talked about. This is a typical sort of assumption. It's true for a lot of SEM models. It doesn't have to be. You can actually do models when this is not true, but this is the basic approach, is that we're assuming that. Because of this, latent variables are also assumed to be normally distributed as well, because they're based on normally distributed items. Okay. There are other techniques to specialize analysis of models with categorical latent variables, which is part of the extended family. You're thinking, what does that mean? Categorical latent variable. We actually have latent categories. It's trippy. The levels of categorical latent variable are called classes, and they represent a mixture of subpopulations where membership is unknown or not known, but is inferred from the data. What? In other words, a goal of this analysis is to identify the nature and number of latent classes. So there's something called latent class analysis, in which you're trying to group people together. This is similar in the idea of what cluster analysis does. Instead of trying to group items together based on their correlations and things, we're trying to group respondents together. Different types of people go together based on their patterns of responses. With latent class analysis, these are people in which their classes are unknown. We're trying to find people who have similar response patterns, and we want to put them into groups. What these groups are, we don't know. We have no clue what they are. We might be able to discover what they are once we sort of figure out who goes together. But these are unknown latent classes in which we're trying to group people together into based on their responses to data that we have them respond to. Okay. So this is called something called latent class analysis. These categorical techniques they have many forms. Latent class analysis is one of them. Something called latent transition analysis. Another term for this kind of thing is something called a mixture model. So the term mixture comes from if you assume sort of one homogeneous population, you oftentimes find out that people don't actually respond in a homogeneous way, right? That what you think of as one uniform homogeneous population really is a mixture of populations or a mixture of subpopulations that make up that population. So what a mixture model does is it tries to uncover what that mixture is. What are the different types of people in there? It sounds very similar to latent class analysis. It is, but it's done in a slightly different way. The way in which you'll see mixture models used the most is in something called a growth mixture model, where let's say you're looking at math ability from 7th to 12th grade, and you want to see if there are different ways in which people grow, change across time. So a growth model is a latent variable version of like a profile analysis, showing we're actually looking at repeated measures data. And you want to look at their growth. You can model the growth of people across time. So growth with mixture combined, you're getting, are there different trajectories? You may have someone who all right, they start off at 7th and they grow, steady all the way to 12th. You may have someone who starts 7th, they grow, they get worse, they have some time where they struggle, and then they sort of grow again. So you have different patterns of growth, and you're actually trying to find out who those people are. And identify the mixture of subpopulations that you have that have different trajectories across that growth model. So these are techniques for estimating continuous and categorical latent variables were once thought to be distinct, like these were separate things. Oftentimes it required different software and things like that. Programs like M+ have combined these techniques together, so you can oftentimes do all kinds of crazy things at the same time, like a multi-level growth mixture. All kinds of stuff can be combined together because this program has made it a lot more, has generalized a lot of the ideas of latent variables into a single program that can do a lot of these things at the same time. All right, so this is, again, just extended family of SEM. These things are all included. What's not included here is you can also do factor analysis or other measurement type models with categorical outcomes or categorical indicators. It's just the problem there is that factor analysis generally requires Pearson correlations, right? It still assumes you have continuous linear data. If you don't, then you need to correct for that. So at a minimum, you need to correct all the fit indices and all the coefficients for the non-normality of your data. Even better is that you actually need to make the correction on the actual the covariances and correlations themselves. You can actually use a different type of correlation. Instead of using a Pearson correlation that assumes everything's continuous, you can use something like a tetrachoric or a polychoric correlation that helps to unearth an underlying continuum for categorical data. And we'll come back to that later on, talk more about that later. But there are other things that fit into this sort of extended family of SEM that we're not going to have time to fully talk about. So the other part, the part we're going to get to towards the end of this semester, is to talk about item response theories. So IRT models are considered latent trait models and differ from SEM models, and that IRT models were developed for non-continuous data. So when I say that SEM models can be used with categorical data, it's because people have figured out ways to tweak it to work with categorical data. But it wasn't designed that way. It was designed for continuous, normally distributed data. And it's just they've found ways to make it work when the outcomes are categorical. IRT was developed for non-continuous data. Right, data that's continuous, data that's dichotomous or ordered polytomous and do not have the typical normal distribution assumptions and all that stuff built in. They started from the ground up thinking we're dealing with items that are either like correct, incorrect, right? They estimate more than just how well an item relates to the latent variable, called the discrimination parameter in IRT. It's similar to a factor loading. You get things like item location and guessing. So my point here is that in SEM, the focus is typically just on the loading or the slope coefficients, the predictions. So IRT, oftentimes the simplest IRT will have at least 2 parameters instead of 1. So with factor analysis, the only parameter we typically care about is what's the loading for this item, what's the loading from this item to this item from the factor. With IRT, there are 1 parameter models, but the typical models are 2 parameters. And so you're starting off with discrimination, which is very similar to a loading, and item location at the same time, which is something similar to difficulty, item difficulty. So those 2 things are brought at the same time, when oftentimes the difficulty of an item, that sort of thing, is not really considered in a typical factor analysis. IRT models were developed to scale individuals on a trait, not to test hypotheses about how variables relate to each other. But I have a bunch of people that are all going to be taking maybe different versions of a test with different items, and I want to be able to put them all on the same scale, so I know who is higher or lower on a trait. Think about your GRE score, your GRE test. ETS uses IRT so that everybody can get a different, even just slightly, but a different version of the GRE. It can be computer adaptive and all kinds of stuff, and they get different items, yet they're able to put them all on the same scale to know who scored higher or lower on the GRE in the different sort of categories. They're able to do that because of how IRT sort of functions, and it was designed to do that. It was designed to put people onto the same scale for a trait like that. That's very different than SEM, that was developed really to look at how items relate to each other and to sort of hypothesize predictions and things, and actually, yes, to collapse items together, but not necessarily to put them on the same scale. You can, like factor scores and things, which is really very similar to what goes on with IRT, but it's still not done in the same way, because IRT uses the difficulty of the item plus the item's discrimination to actually put people on the same scale, where factor analysis doesn't have that as much information when putting people on a factor score. Where SEM models can be thought of as the combination of multiple regression and factor analysis, IRT models combine logistic regression, factor analysis, and a little bit of item analysis, like test theory, like again talking about items, discrimination, and difficulty, and those kinds of things. In many ways, this distinction is becoming more and more blurred. I mentioned this before. And IRT models can be converted between them. Also, many programs can estimate both. M+, again, can do both within the same sort of framework. SEM and IRT also share many traits in terms of they both look at things like model fit. They both have similar kinds of estimation procedures, like they rely on things like maximum likelihood. They do produce scaled scores, factor scores in SEM, and the scaled scores in sort of IRT. They both are confirmatory processes, and they both require sort of large N to do. IRT and SEM differ in that IRT was designed for non-continuous data. IRT models can require up to 4 separate parameters per item to estimate a model, as opposed to the 1, right? So in SEM, it's like slope or loading, usually for an item, that SEM measurement models require, right? IRT is also measurement without inherent structure. And so it's just measurement. We don't typically test for structural things in IRT, even though you can. There's no structural regression type models without some extra steps. You can actually scale folks into a common scale, create that value, sort of like a factor score, and then use those to test for structure, to look for predictions and things like that. But that's not typically what IRT is for, even though it can. Just oftentimes it's used for scaling. So some jargon, you got the item response function, the IRF. It's the mathematical function that relates an item to the latent trait via estimated parameters. So things like item location and discrimination. These will look somewhat odd, but also familiar because they look very much like logistic regression because they are logistic functions. Okay. Then you got the item information function. We can take the item response function and we can convert it into an information function. So it's an indication of how good the item is doing. So in multiple regression, also in factor analysis, we look at things like the squared loadings to look at how much of the commonalities and things. In regression, we look at things like the standard error of estimate to see how well is our model doing prediction. This is sort of similar in items ability to differentiate among respondents. It's similar to standard error of estimate in multiple regression, but it's not a fixed value. It actually tells us that there are places on the latent trait where we do a better job of predicting and places where we do a worse job, so it's actually not a fixed constant. It actually is a variable that changes depending on where you're trying to estimate. And you got item characteristic curves, which takes the item response function and sort of is able to project out what the probabilities would look like based on the item's parameters. So this is a logistic type curve that connects the latent trait that we're going to call, again in IRT, it's called theta, to the probability of endorsing an item. So I use the term endorsing because it's psychology. When these were developed, it was the logistic type curves that connect the latent trait to the probability of getting an item correct, because it was done for things like testing. So how likely are you to get an item correct based on your trait level and the difficulty of the item? So I'm saying endorsing here because we don't think about answering items on a depression inventory as getting them correct. If I say yes to a depression item, I'm endorsing it, not getting it correct. So I'm using this more generically, but they all mean the same thing. All right, it's all different terms from different places, different fields that really are referring to the same phenomenon. All right, so item location is analogous to the item's difficulty, right? And is the amount of the latent trait needed to have a 0.5 probability of endorsing the item. What the hell does that mean? So think about if the latent trait is math ability, right? How much math ability I have. A difficult item means that I have to have more math ability to get that item correct. An easy item means I can get the item correct with less math ability. So that's why it's the place on the latent trait where I need to be to get a 50-50 chance of getting the item correct. If that is higher on the latent trait, if I need more of it, that item is more difficult. If I need less of it, the item is easier. Okay. We also have the item's discrimination. So how strongly related the item is to the latent trait. It's like a loading in a factor analysis, and it indicates the steepness of the item response function at the location. All right, so what does that mean? It's the same thing like factor analysis. The higher the loading, the more that item relates to the factor. This is the same thing. The higher the discrimination parameter in IRT, the more that item relates to the trait you're trying to measure. So the more discriminating an item is, the stronger it is related to the item. So what you want is items that are very discriminating, have strong discrimination, but vary in difficulty, so you can actually cover a wide range of the trait that you're trying to measure. So here's an example item characteristic curve. So if we look at right here, the latent trait oftentimes is written out this way. This is theta, right? It's written out as sort of a z-score scale, right? It's just a arbitrary mean of 0, varies in single units, standardized like that. If you look at where 0.5 is on the probability and come over here like this, where that point is, and I drop it down, that means that 0 is this item's location. This is sort of middle of the road in terms of difficulty, right? It's targeting people that are right towards the average of whatever this is. Again, imagine this is math ability, okay? Imagine this is, if this is depression, I'm sort of in the middle. Average depression is what this item seems to be targeting location-wise. Discrimination-wise, it has a fairly steep slope here right at that point. So it's fairly discriminating, and it has a location of about 0. So So here's two items that are the same discrimination, different locations. So which of item 1 and 2, which item is more difficult? Hopefully, you said item number 2, because item number 2 requires that you have more of the latent trait to have the same probability of endorsing this item or getting this item correct. If it's math ability, it means I have to have more math ability to have a 0.5 chance of getting this item correct. If it's something like depression, I have to be more depressed to have a 0.5 chance of endorsing this item. Or this item, I am at the same probability at a lower level of math ability, a lower level of depression. These are different discriminations and different locations at the same time. So of 1 and 2, which one's more discriminating? 1 or 2? So hopefully you said 2 again. It actually is more, it has a steeper slope. So it's more discriminating than 1 whose slope is slightly, wow, it's hard to say, slope is slightly less steep going that way. And again, item 2 also seems to be slightly more difficult because of where the 0.5 is sort of hitting each of the curves. All right. Here we can look at, here's 3 different items. And you can ignore this for now, but I will mention what these numbers are talking about. So you got 2p, 3p, 4p stands for 2 parameters, 3 parameters, 4 parameters. We'll talk about what those parameters are later on. Well, at least the 2 and the 3 we'll talk about. We're probably not going to talk about the 4. But this talks about how many parameters are needed to estimate these items sort of correctly. You can see that the item in the middle, this one was sort of the dots here, super steep, very discriminating. This one is also pretty discriminating, but slightly less so. This one's pretty discriminating as well, but this one is far more difficult. All right, the location's much higher. I have to have a lot more, whatever this trait is, to have a chance of answering this question correctly. This one, is targeting sort of right here in the middle someplace, and this one is sort of a much easier item. So the way that the reason I have these things out here is because when I mentioned information, item information, tells you sort of the quality of the item, but also who the item is really targeting, at least in terms of the trait level. So the steeper an item, the more discriminating an item is, the higher, the more information there is, but it's more information for a narrower group of people. The lower the discrimination, the wider the information gets, but it also gets lower. So you're getting less information about more people, where a steeper slope gives you more information about less people. So to illustrate that, this is what's called an item information, or these are item information curves that correspond to the 3 items. So the one that was easier, obviously, is targeting people who are farther down, because its slope was lower. It actually has less information relative to the one in the middle that was super steep. So this one gives us a ton of information about people that are right in the middle of the trait. This one gives us less information, but it does so about a wider range of people on the top, and this one does a wider range of people on the bottom. So this is why I was saying earlier that you oftentimes want items to be discriminating, but you also want them to vary in difficulty, because if you want to be able to differentiate between people at the top, be able to tell these people apart from one another, you need an item that actually is targeting that differentiation and has some decent amount of information to be able to tell you that. The same thing, you want, all along the trait level, you want to have items that are targeting different levels of the trait with enough information, with enough discrimination to really tell you something about how those people are differing, and be able to scale them and tell them apart. Someone who is just below sort of clinical depression versus someone who's just above, you need to be able to differentiate between them, or else you're going to make mistakes and sort of classify them or scale them in the wrong place, because you don't have don't have a questionnaire that is sensitive enough to tell them apart. So that's how we get to sort of item information. And we can actually take, I didn't include this, but you can, I mentioned this was related to sort of standard error. You can actually use this information to create a standard error curve that will tell you where you're doing the best prediction. So like based on this item here, you can actually see the standard error for that item would be right somewhere near the zero. You're going to get the lowest amount of standard error possible, because that's the best place that you're getting the most information. And then it's going to go back this way, and you're going to get more standard error as you try to predict people who are outside of this range. So if all this stuff is sort of going over your head, it's fine. This is meant to sort of, here's some information, and so you hear it the first time, sort of let it sort of wash over you, and then when we come back and revisit it in more depth later on, it'll sound familiar, and then we can sort of talk about it and go more into it, as opposed to sort of springing on you the first time at that point. So here's a short introduction, and then we'll come back to talk about a lot of these things in a lot more detail as we go through the semester. So that's it for the introduction, and we will talk more. We'll start doing a review starting in the next sort of section. All right, that's it.